Ever feel like analyzing complex RLC circuits in the time domain is a challenging puzzle? You are certainly not alone. The intricate dance of resistors, inductors, and capacitors often leads to differential equations that can be quite tricky to solve directly. Performing the inverse Laplace transform for RLC circuits is the crucial step that takes your simplified circuit solution from the frequency, or S domain, back into the real-world time domain. This process allows you to understand exactly how voltages and currents behave over time, providing the practical insights you need for circuit design and analysis. The core reason we use Laplace transforms in the first place is to convert those challenging linear differential equations into much simpler algebraic equations in the S domain. Solving these algebraic equations for your circuit variable, like voltage V of S or current I of S, is significantly easier. However, V of S or I of S does not tell you what happens when you flip a switch. The inverse transform is therefore essential to bridge this gap, translating your S-domain solution back into a familiar time domain function, such as V of t or I of t. To skillfully perform the inverse Laplace transform, you typically follow a clear sequence of steps. First, ensure your circuit variable, for example, V of S, is expressed as a rational function, meaning a ratio of to polynomials. Next, if the denominator polynomial has factors, you will need to apply partial fraction expansion. This technique breaks down complex fractions into simpler ones, which are much easier to work with. Remember that the roots of the denominator polynomial, known as the poles, will dictate the specific form of your time domain response, whether it includes exponential decays, sinusoids, or damped sinusoids. Finally, you will apply the standard inverse Laplace transform pairs to each of the partial fractions, converting them directly into their corresponding time domain expressions. A valuable insider tip for RLC circuits is to recognize the significance of critically damped, overdamped, and underdamped responses directly from the poles in your S-domain solution. Distinct real poles indicate an overdamped response, while identical real poles point to a critically damped one. Complex conjugate poles, on the other hand, reveal an underdamped oscillatory response. Understanding these relationships saves time and helps you anticipate the circuit's behavior before even completing the inverse transform, offering a deeper diagnostic capability. Ultimately, mastering the inverse Laplace transform not only solves your current circuit problems, but also significantly enhances your predictive capabilities. It allows you to confidently move between the mathematical convenience of the S-domain and the practical reality of the time domain, empowering you to design and troubleshoot RLC circuits with a profound understanding of their dynamic responses.